Welcome to third session today. In the third session, moderators are Associate Professor Gökhan Kirkil from Kadir Has University Center for Energy and Sustainable Development, and Dr. Okan Yardımcı, who is energy expert in the Republic of Turkey Energy Market Regulatory Authority. Dear professors, welcome. At the end of each presentation, our moderators will evaluate, and you, dear audience, you can write your questions to the chat part by specifying the person you ask your questions. At the end of the presentations, our moderators will ask questions on your behalf in our discussion part. And the first presentation from Shan, Kadir Has University. The topic is energy storage systems, characteristics and comparison.
Yes, Hujam.
Ali, screen is yours.
My name is Shan, and today I will present energy storage system, the characteristic and comparison. I'm from electrical department and I am doing PhD here. I don't know what's now. It's like it's not working. Sorry. So first of all, I need to explain what is the purpose of my presentation and what I need to do and what I will explain. Purpose of presentation is to compare different energy storage systems. And at the end, we will see that which one is more economical and which one is easily available for everyone. So this is the main purpose of my today presentation. So for today's presentation, I will come to the storage system, but before why we need storage system and how it will help us, let me talk about that one first. So I will start from sustainable energy transition. So and now that we are entering to a new area called sustainable energy transition. This transition is also in the first transition come like from wood to coal, we transit in the very beginning of the energy. If we think we transit from wood to coal and then from coal to fossil fuel and so on. But nowadays we will transit from fossil fuel to renewable energy. But again, if we transit, why we need to transit from fossil fuel to renewable energy? We have three main issues in fossil fuel. The first one is not distributed equally on the surface of the earth. It's not equally distributed everywhere on the earth. And we are using it very fastly and it's very limited. And the most important one is creating a lot of environmental problem and climate change and all these things. So all these, because of these three major problems, we have a lot of other issues also, but we will only these three major problems we will take into account. Now, how we will get rid from fossil fuel? So the first one, increase the share of renewable energy to our current system. As you know that there were two international agreements. According to two international agreements, one is Sustainable Development Goal and the other is Paris Agreement, which was held on 12 December 2015. The main goal was that we need to bring carbon emission up to 0% until 250. So how is possible? But still, we will do it. But in renewable energy, we have two more issues. One is intermittent in nature. It's not available like all the day. For example, if we consider solar energy, it's only available when there is a sun or in a sunny day, just like wind energy and all these things. Also, it depends on the geographic and climatic condition. If climatic condition is changed, the output from renewable energy it definitely change. Same is the geographic location. For example, it depends on the altitude, that on the sun and wind and all these things. So next is, so what is the solution and how we will cope this, the use of fossil fuel? The solution is storage system. So we will store this renewable energy and then we will use whenever we need. So there are different storage technology. The first one is pumped hydro storage, compressed air energy storage, battery, superconducting magnetic energy storage, flywheel, capacitor, and supercapacitor. So the first one, if you can see my screen, the first one is hydro pump hydro storage. So in pump hydro storage, it mostly widely implemented in a large scale of electrical energy storage system is shown in the diagram. Such a system is normally consists of two reservoirs. One is the upper reservoir and the other one is lower reservoir. So two reservoirs located at different elevation. A unit are pumped to the water to the high elevation to store electricity in the form of hydraulic potential energy during, for example, when there is in a night or a weekend, if we don't need such amount of energy, so the price of energy is low, so we can use that low reservoir water. We can use pump and we bring that water from low reservoir to high reservoir, and when there is a demand like peak hour, then we can use again and we can convert the potential energy of the water into electrical energy. Same is like compressed air energy storage system. In compressed energy storage system is another commercial available technology. It's almost same like pump hydro storage, but there is some difference. We have different component like motor, we have compressor. Actually, we are storing compressed air storage, and then we are using that when we need. The third one is battery storage system. And battery storage system is like we know battery from the very rechargeable secondary batteries is the oldest form of electrical storage energy. So what we are doing with electrical energy, it's actually a battery consists of one or two or more than electrochemical cell, and each cell consists of liquid phase or solid electrolyte together with a positive electrode, anode and cathode and all these things. Actually, we are converting this, we store energy in the form of electrochemical energy or in the form of chemical energy, and whenever we use it, whenever we need, we can use it. The third one is flywheel. So flywheel, it's another form of energy in which we store, like if you can see the screen, there is like upper magnet bearing, there is axis of rotation, we have generator, motor, rotor, protective shield and all these things. The main thing is we are storing energy in the form of, here we are storing energy in the form of this rotor. We can apply by using motor or generator, and we can just rotate the rotor, and then we can store this kinetic energy after we can use it. So this one is flywheel, and the other one is super magnetic energy storage. And super magnetic energy storage, its work, just you can see the coil in the red color. We can pass the current here. Like first of all, if I need to explain the superconductor, there is no resistance. Resistance is zero. So if we are using to store, superconductor is the known technology to store electrical energy directly into electrical current. Store electrical energy is a direct electric current passing through inductor made of a superconductor material in a circulator, so that the current can circulate independently with almost zero losses. If there is no losses, so it's not possible that we can lose our current. So we can store this in the form of magnetic field. We can store that energy, and whenever we need, we can use it. The other one is it's a supercapacitor. So capacitor is the most direct and a lateral way of storing electrical energy. With the capacitor, it's a very simplest form. One is the positive plate and the other one is negative plate. And between we have some dielectric material. It's like an insulator we can place. So if we need a high amount of energy, we will use this dielectric according to our requirement. So now we will compare all these. It's a comparison table, and we will see that which one is good and how we decide that that one is good. So if we can see the table, comparison table, pump hydro storage energy, power rating, discharge time, self-discharge per day, suitable storage duration, that for how much duration we can store our energy. We can store it for a month, per hour, like, and so on. And what is the effect of the storage energy on the environment? And the last one is capital cost. So if we compare all these one, pump hydro storage is the best one. But And also hydro storage capacity around the world, if we can see, they are using it now, like China, they're using 36390. It's in megawatt. The capacity is in megawatt. The second one is United States, then Japan, Germany, India, South Korea, and the last one is United Kingdom. So in a conclusion, according to our study and according to all these things, electrical energy storage is needed to everyone. Without energy storage system, it's not possible that we can use renewable energy efficiently. The second one, energy storage technology, we are not using this only to store energy. We can also increase the power quality. We can also increase the reliability of a system and all these things. And according to our study, it's not possible that only a single storage system can meet all the requirement of an ideal electrical energy storage system. So here I will explain that why I'm talking about this, that not a single storage system. For example, if we can consider a flywheel, as I said before, that a flywheel, we can use flywheel for a very short interval of time. If we need like a transient or something like this, we will use flywheel. So we cannot use flywheel for a large demand, or like if we need energy for a large time, then we will shift to hydro pump energy storage or with other systems. So we need to study on these things, but only a single system at a time cannot meet all the requirement. So, and also we say that according to our study, we realized that pump hydro storage is the best one, but still we need to do some research on that side, and still it needs a lot of improvement. Like the one example I will take, that the pump like reservoir, let me show you the screen again. If you can see this one, here is one is pump and the other one is generator. So sometimes we are using a single motor, a single machine is a generator and is a motor. So it's definitely efficiency is not so good. For example, if we are using synchronous motor is a generator and is a motor. So synchronous motor, it will work best if we use is a generator, but efficiency will not best if we use a motor. For example, induction motor. If we use induction machine as a motor, its efficiency will be good. But if we use induction motor as a generator, its efficiency will be not good. So we need to think about these things. And the last one is the cost, the capital cost is so high and the environmental effect. So we need to think about it, how we can decrease the cost and how we can minimize the environmental effect of the hydro system. Thank you so much for your time.
Thank you very much, Ali. Gökhan Hocam, would you like to start first?
Yeah, thank you, Ali, for your presentation. I think it's interesting to know and then compare these different energy storage technologies. Yes, I think in your table you listed the capital cost, but I think also it's also important to know the operating costs of all these technologies. I know it's hard to compare. And also important to know the future prospects, like which some of, as we have seen with the PV technologies, the capital costs decreasing very fast in the future. So in the 2030, 2050, we would like to know the cost of these technologies will decrease, how fast they are going to decrease. Therefore, their performance is going to be important.
Yeah, Hujam, can I add one thing? Like you are talking about the PV cell, but here we are talking about the energy storage system, not a generating system. So that's why I know we didn't focus on these things that either PV will be better, or like we are only talking about the storage system, not a generating system. And thank you so much. I will correct these things.
Yeah, probably their cost will also decrease, I guess, in the future.
Yes, Hujam.
That's what I was talking about. Okay, thank you, Okan Hocam.
I now realized that I am.
Thank you very much. Since this is the first presentation of the session, let me convey my greetings and congratulations for the organization of the event. So it's a very well-organized event again. So first of all, Hazal Hocam, the other organizers of the event, congratulations for this great program. And Ali, that's a very nice presentation. Thanks a lot. Could you please show us the comparison table again? That slide.
Yes, Hujam.
Could you please show us the comparison table again? The slide that.
Can you share the screen again?
Yeah. Yes, Hujam.
Yeah, that's a very nice slides. And how did you get the data? Did you combine by yourself? That was my first question.
Hujam, no, I use different, like the one which I use, this data I get from a Science Direct. This is one journal, so I get it from here. I will put maybe I don't put reference of this thing, but I use elsewhere like Science Direct. So from different sources, so you combine together.
I believe in your final paper the sources will be also there. And as Gökhan Hoca mentioned, yeah, it's very good to see a comparison for OPEX as well. And as you know, yeah, that was very great to see the pump up system, batteries, flywheels, magnetic systems, the comparison of them in regards of capex. But what I was looking was also the legal aspects. You know, in Turkey, there's a very significant development in the recent weeks about the storage system, and it's incentivized with the renewable generation. The renewable generation will be exempt from the license in case of installing a storage system, something like that. But these systems have what I wonder, are they aligned with the all aligned with the renewable systems, or are there any differences on behalf of that? That was my question. Did you had any search about that, or just you compare by?
No, like we didn't mention the legal way or what you're talking about. Just we compare all these things like this way, and just we consider like environment and all these things. But regarding that side, what you are talking, we didn't study on that side. So
no, that's okay. You focused on the technical comparison. Yeah, that's very good. Maybe you can allocate a kind of.
And I will add, like it's a good point that I will add also the legal point so that we can move it further or like something. So it's better that we can do it also.
That's great. Thank you very much. Thanks for this presentation.
Thank you so much.
Şener Hocam.
Okay, thank you very much, Ali.
Yeah, Hocam,
the question is it your subject? Is the subject for your MSc thesis?
No, Hocam, it's like only a subject. It's not a research topic. It's just like a normal. Actually, we are doing a coursework, so it's one of my course subject.
Okay.
Yeah.
So in your course subject, you are really looking into energy storage systems.
Yes, Hocam.
And you expressed in the first slide or so, you need the energy storage systems to get the renewables really feasible or for the future.
Yes,
do you have any feeling that what is the level of renewables you can integrate to the system without a storage? Did you do any sort of simulation? what is the level you can really integrate renewables to the system without a storage, where you should be start really thinking of storage?
Jim, the main thing is like, as I said before, and I take example of a solar energy. So without storage, so how it's possible that we can use solar energy with a high efficiency? For example, if there is no sun.
My question, Ali, we are using solar energy without storage in Turkey. Many countries using solar energy without storage, just integrating to the system network. What is the level of this power you can include in the existing network for renewables? That's the question.
Oh, Jim, now I realize your question, but I'm really sorry. I don't know how much, I don't know the exact figure and all these things. So I realize your question and I understand now that what you are talking about.
Yeah, the other question really, okay, so you listed pump storage, batteries, flywheels, etc. But those are all technologies. I think the detail I wasn't very much satisfied with. For instance, when you go to batteries, what are the existing battery types? Are we talking about a simple lead-acid batteries, or are you talking about lithium ions or other alternatives? When you think of storage, you must need really to look into a little bit deeper.
Yes, Hujam, like for in presentation, I just mentioned a battery, but in battery, if we can see, we have a lot of like lead-acid battery and all these things, but mainly
you can enrich your slides by putting those down.
We have a lot of type, we have a lot of variation in battery. Yeah, you are right, Hujam. But just like I just consider the overall image of a battery. What like if battery is from any material, the process and the main principle will be same. So just I took a whole picture of these things. But there is a vast explanation on battery. You are right, Hujam.
It's a good presentation, but it could be enriched by putting some references, as Okan Yardımcı said, and you could really make it a little bit better. Thank you.
Thank you so much.
And a small following comment after Şener Hoca. Yeah, the contribution of these technologies to solar and wind resources can be different. You know, in general, storage systems can improve the solar generation in a better way, but you can also add that part, you know, how the different system, these different storage systems can contribute to different renewable energy sources. This comparison can be also very nice to see in your research.
Yes, definitely I will do it.
All right, thanks.
Definitely I will.
Thanks a lot.
Thank you, Ali.
Thank you so much.
Next presentation is the shift to electric vehicle and its effectiveness in reducing carbon emissions by Mustafa Omar Mohammed Nabil. By the way, dear participants, please keep your presentation in 15 minutes. And Mustafa, screen is yours.
Good afternoon, everyone. Okay, so I will try to keep this short. My topic is titled "The Shift to Electric Vehicles: Effectiveness in Reducing Carbon Emissions." My name is Mustafa Nabil, and I am in the computer engineering department. I'm currently doing my master's, and I took this topic as one of the course projects that to conduct this topic. First of all, I will try to give you a brief overview of what I aim to discuss. I'll give a background. I'll start with the background on my topic, and then I'll zoom in on the problem statement. I will highlight some of the contributions that this research aims to achieve. I will discuss a few key literature points. I will talk about my methodology, and finally I will conclude. I must preface this presentation by saying that due to the limited time, I had not been able to finish the project as a whole, and so it is currently ongoing. It's in the ongoing process. To give a background and to highlight the significance of the problem, the transport sector is one of the largest global carbon emission, and it's of course dependent on the geographical region, but it does still have a very large impact on global carbon emissions. There were several efforts for most of the history of internal combustion engine vehicles. For most of its history, it has been reliant directly on fossil fuels, and that has contributed, largely to the carbon emission levels in the atmosphere. And likewise, like the transport sector, there is the power and generation sector, the agriculture sector, all of which contribute largely to the overall global carbon emissions. Now, a strategy that was used, or that has taken focus in the past 2 decades, was actually to electrify transportation. And that shifts the problem from attempting to get carbon emissions across different sectors to zero, rather than just focus on the problem of transportation and the problem of power, electricity generation separately. We can now focus on solving the problem of electricity, since the transportation sector would be completely running on electrical power. And that's the underlying idea with the electrifying transportation. And so we have seen quite a lot of a push towards adopting electric vehicles in several countries, with China now leading, and EU the EU countries coming in second place. Of course, this all with an attempt to reduce global carbon emissions and reach to a net zero carbon levels. And there were international agreements such as the Paris Agreement, and likewise you have internal policies that aim to satisfy or to reach that target. And some of these policies, as I highlighted in the second point here, is that lower taxes, free parking, and other incentives have been used to push the public, and as well as the private public, as in the individuals as well as corporations, to move towards electric transportation systems and electric vehicles. This is a chart from the report that's showing the breakdown of how the proportion to which carbon emissions, the proportion or the division of vehicles that contribute to carbon emissions in the EU. And as you can see, most of it are from road transport and from cars, which is why I aim to focus my project on looking at policies that specifically target the road transportation users. So to zoom in on the problem statement, I would like to ask the question: have these policies, strategies, and interventions been effective in reducing carbon emissions, and to what degree have they been effective? So we've been implementing several policies throughout the past decade, in attempting to increase electric vehicle penetration into the sector. And the question is, how effective have they been in reducing carbon emissions? So with this research, I aim to answer the following questions, and although some of them are quite broad, I do hope that this would contribute in some way or another to these questions. Firstly, whether these policies that are implemented, across different geographical regions, do they align with the targets that have been set for a net zero carbon emission world? And moreover, what are the challenges that are faced with adopting these policies and implementing them? And how have these policies evolved over time, perhaps over the past 2 decades throughout this journey towards the target we want to achieve? Moreover, how do we measure the progress of EV policy in reducing CE? Once again, of course, it is slightly a broad question, but if I can address at least part of these questions, that would, I think, be a decent contribution. What are the acceptable trade-offs associated with policy adoption and implementation? And again, specifically narrowing it with EV or electric vehicle policy. Moving on, I will highlight a few key literature that I looked at, so that will highlight that will compare electric vehicle policy and its effect on reducing carbon emissions. So a study was run in China, looking at their policy to promote a move towards electric vehicle, and 16.3% reduction annually per capita was noticed. That was a study that was conducted in 2022 by Zhang and others. The second point highlights a study that looks at how a policy that incentivizes the use of electric vehicles could actually reduce or eventually result in reduction of carbon dioxide emissions by up to 85%. Study conducted by Zhang in 2021. The third study is quite interesting, actually, which is why I will spend a little more time in explaining it. This study was run in China over 31 provinces, and they did a life cycle analysis looking at how the use of or how the adoption of electric vehicles in these different provinces can assist in reducing carbon emissions. And it was interesting to find that this was strongly linked to the electricity mix in that province. In about 3 provinces or 3 regions, the comparison between internal combustion engine vehicles and electric vehicles in reducing carbon emissions was not that significant, simply because of the electricity mix. And as we are aware that China is still heavily reliant on coal for its electricity generation, or at least in many of the provinces. And of course, that if we consider the life cycle of an electric vehicle, and throughout its life cycle, the carbon emissions that it has compared with an internal combustion engine vehicle, but the electricity mix in that region is actually heavily reliant on fossil fuels, then we would not see that much of a significant improvement with the adoption of EV. Finally, the fourth study, which was also quite interesting, the study looked at how traffic flow, or the study suggested that traffic flow actually has a large contribution or contributes largely to carbon emissions with internal combustion engine vehicles. Having traffic in a particular place would actually increase the carbon emissions produced by internal combustion vehicles. However, replacing that with electric vehicles, they found that despite the increase of traffic and the traffic congestion, despite all this, that would still have a reduction in carbon emissions. And so they suggested the implementation of policies that push towards the adoption of electric vehicles in highly dense and highly populated regions, and to allocate resources in prioritizing high traffic situations or high traffic regions first before others. So that is with regards to the literature, these 4 key literature. Of course, I realize that there is still a lot to look at. And as I mentioned earlier, due to the time limitation, I had not had the opportunity to do that, but there's still a lot to do with regards to reviewing the literature. As for the methodology I aim to conduct this study with is to start by classifying all the literature in the past decade, or perhaps the past 2 decades, and to categorize them based on geographical region, after which I can assess them and assess certain important metrics in trying to answer the question, how successful has this policy been in this specific region, this electric vehicle policy, and maybe looking at the factors that contribute to the success or failure of a specific electric vehicle policy. Now, I also realize that if I can find some way of quantifying these measurements rather than have them qualitatively conducted, that would also improve the research and maybe perhaps give it more value. I will look at things such as carbon emission changes throughout this period, also how EV penetration in a specific sector or region has also changed throughout that period, and what are the associated costs with implementing those policies in those regions, and perhaps also a comparison across different regions. To conclude, I talked about how electrification of the transportation sector can reduce, or there's sufficient evidence to suggest that it does reduce carbon emissions. I will, of course, have to look at geographical regions, how it influences and affects, the carbon emissions, and then, moreover, I hope that this will contribute to the literature and the corpus on sustainability, electric vehicle policy, and environment as a whole. That is it for my presentation. I thank you very much, and I welcome your criticism and feedback.
Thank you, Mustafa. Okan Hocam, would you like to start first?
Please.
Yeah. Gökhan Hocam, buyurun.
No. But I thought he said Gökhan Hocam. I think Okan Hocam. Okay.
All right. My friend, first of all, a very timely topic. Congratulations for that, because as you all know, Turkey is also trying to enhance the EV ecosystem and incentivize EVs, EV infrastructure, charging infrastructure. So I thought it is a very timely topic. And that was very good to hear that you mentioned the electricity mix. That's very good because it affects a lot. Whether we produce from coal or natural gas or renewable energy sources, 100. On the other hand, there is also a big distinction in the literature. There can be huge differences depending on whether the manufacturing process of the vehicle and the battery is included or not. According to some assumptions, the negative effects of the manufacturing may be more of the batteries and the EVs. If you are considering just well-to-wheel, it shows us how the EV is efficient comparing to the internal combustion engines. But when you consider the manufacturing process, especially the CO2 emissions can be very bad. So what I highly suggest to add the manufacturing process as well as a subtopic maybe. I have a report on that. It's not publicly available right now, unfortunately, the World Bank report, but I can mention that part. Yeah, when you are considering the manufacturing process of the EVs and the batteries, the CO2 emission picture can be different. So that's my suggestion. Congratulations for your presentations.
Thank you so much, Okan Hoca, for your valuable suggestions.
Gökhan Hoca.
Yeah, thank you, Mustafa, for your presentation. I agree with Okan Hoca regarding the emissions. If we just consider like in manufacturing sector, they call this scope 1, scope 2, and scope 3 emissions. So if you just consider the emissions resulting from use of electric vehicles, yes, it's decreasing. But if you're considering the scope 2 emissions, how do you generate electricity to run these vehicles? So if it is still they are still from fossil fuels, then it may even increase. In some studies, they are saying that it's even increasing the total emissions. Even you also add the scope 3 emissions when you consider the other, for example, what do you do with the used batteries? So how do you get rid of them? And if you consider all of these, so there are lots of discussions in the literature about the total emissions. And then it's also good. It's also need to consider the charging stations, availability of charging stations. I mean, we can produce millions of cars and we can put them on the roads, but if we don't have the charging infrastructure available, then it may not be practical to. So they should go side by side to each other. So we need to also provide charging stations and necessary infrastructure to use these technologies in a wider sense. So those are my comments. Congratulations again.
Noted, thank you.
Thank you very much.
Can I say a couple of words to Mustafa?
Sure, Hajam.
Okay, Mustafa, if you go a couple of slides back for your references. Okay, it's quite nice. Zhang et al. Where can I find it? There's no reference page in your presentation.
That is true. That is true. I think I should have clarified.
221, and most of your references are from China. Europe, as you know, has significant amount of study on this matter, because as Okan Hoca suggested, it's a hot potato now. Everybody's talking on it. Yes. And when you really enter this kind of field, probably it might be worth mentioning vehicle integrated photovoltaics. How much really extra mileage you might add up with the integration of photovoltaic onto vehicle might be a good way to look at, as well as, when you look at the electrical vehicle, it's quite again hot subject. Many companies has those already on the road. For instance, in Germany, they've got the sonar cars on the road. Really, with this might really improve your presentation if you include vehicle integrated photovoltaic.
Vehicle integrated. Okay, noted.
And I suggest you should go through the actual work of EU, the International Energy Agency's working group, PVSEC, PVPS. And you should look into that really. There's very interesting recent publications on those, as Gökhan suggested, how you really design the charging station and how you can do that, how you can really handle with renewables, etc. I suggest really you should go look at the Europe as well. But the first thing, again, I'll repeat, please put a reference slide at the end.
Absolutely, for sure. Thank you so much for your
Thank you.
Next presentation is Büşra Çelik's. The topic is simulation-based analysis of fuel stations and outlook for the integration of EV charging units towards sustainable cities.
Now we talk about simulation-based analysis of fuel station and outlook for the integration of EV charging units towards sustainable cities. We are undergraduate student at İstinye University, and this project is supported by TÜBİTAK 2209A. We have included 10 content in our study. First one is research summary. In recent years, within the scope of the sustainable concept in transportation, the incentive, the use of the electric vehicles has been increasing to minimize the damage caused by fossil fuel vehicles to the environment. The growing use of the EVs raising two important issues. First one is integration of charging units, and second one is position of hybrid station. On the other hand, since of the use of the will be decreasing, another significant problem appear regarding the future of today's fuel station. Therefore, the conversion of fuel station into hybrid station comes into question. Both do contain serving PVs and adapt to the EV transportation with the providing charging units in central location. What is the purpose of this study? This is our main question. Our purpose to prepare a simulation study that can serve as a stepstone before the conversion process to hybrid station by making a detailed analysis of the performance measure of the conventional fuel station. Let me talk about the stage of this work. First, a typical fuel station is examining in detail terms of component and process flow. Then the model assumption and input model are determined clearly, and computer model that accurately represent the fuel station is constructed using the simulation software. Next, a verification is made in which the key output variable are compared to the test, and the theoretical model is corrected represented in computer model. After the model is verified, convenience interval for the output are established. Then scenario and sensitivity analysis are performed to explore the impact of input variable on system output. It is conducted. The study could be used as the initial study in the transformation process, the hybrid station, and it could be extended by converting the prepared model a parametric model in this feature studies. Another title is Background and Motivation. Most of articles in the literature have emphasized that fuel stations are a good alternative for the position of EV charging units, and studies has been carrying out on this subject. However, many of these papers generally focus on the structural adequacy of the station in the conversion of fuel station, the hybrid station, and didn't touch on the effect of the transformation on the operating system of the station. Some of these studies are as follow. First one is Chai et al. Conducted a case study using large-scale data for the public charging station planning and experimented with different scenarios for the installing charging units and conducted the gas station-based charger are more suited to consumer habits. Second one is Miralaniki et al. Suggested the gradual conversion of existing fuel station into charging station for EVs by analyzing consumers' purchasing trend and road choices and the location of EV charging station and PV refueling station. And third one is alternative scenario for the integration of EV charging units at the gas station were tested by Mauri and Velsiki, and they come to conclusion that existing gas stations are accessible a location to install charging system.
Fourth one is Tang et al. Proposed an optimization model for the position of EV charging units by considering different factors such as passenger priority, passenger distribution, mileage, and EV distribution, and evaluated the effect of these variables on the position of the station using simulation and ANOVA technique. They noticed that variables other than passenger priority had an impact on the layout. Fifth one, Zuhu et al. Stated that the location and capacity of EV charging station are very important for planning and calculated the capacity of charging units using the queuing theory and taking into account the randomness of the arrival of vehicles to the station. Models that optimize the charging capacity according to the traffic condition, user waiting times, and distribution was developed using MATLAB. And conceptual model, our conceptual model has 6 pump islands, while 4 of the pump islands have 2 pumps, and 2 of them have 3 pumps. And 10 of these pumps provide diesel and gasoline service, and 4 of them provide LPG service. And our customers can visit the gas stations to refill or to both refill and shopping, and they have two type payments like cash and card. And in the area, there are 6 workers serving 14 pumps and 2 workers at the store. So the system performance is affected by worker ability as a secondary sources. And model allows for performance analysis for the various scenarios taking into the account different servers of capacities. And we have some performance metrics for analyzing like utilization rate, timing system, timing queue, numbering system, and non-billing queue. And simulation model structure, these 2D and 3D computer models were prepared using simulation software. And in simulation models, the input parameters are defined with the exponential distribution like inter-arrival time, setup and tier time, refueling time, service time of convenience store, and also some probability values are defined for cash and card payments. And model verification, why was it done? Because it was done to see if the main output and performance measure of the computer model were consistent with the result from the base theoretical counterpart. And how was it done? There are 2 interconnected systems in the model because service availability for customer depends on availability of pumps and workers, and therefore the MMCQ model representing the overall system and MG1Q model representing the subsystem were developed. What was the result achieved? It has been concluded that the output values obtained from the theoretical model were within confidence intervals and obtained from the simulation. And we output analysis. We made some output analysis because accordance with the result of the performance criteria determined from the for the interpretation of the operation of a typical fuel station, and it was aimed to establish confidence intervals for the actual performance output of the system. And in summary, confidence intervals were improved for each output by taking the significant level alpha as 0.01 and performing 25 replications.
Scenario and sensitivity analysis. To investigate the impact of input variables on the operational performance of the fuel station, scenario and sensitivity analysis were performed. The operational performance of the system was measured by the outputs mentioned in Table 1. There are 2 types of the input variables, namely uncontrollable and controllable. Uncontrollable ones depend on the customer behavior, like inter-arrival time, pump selection of the customers, refueling time, and payment method of the customers. Controllable ones depend on the system elements, like worker service time and worker service discipline. In scenario analysis, 2 different types of the cases were defined. While case 1 is about the distribution of the customers, and case 2 is related to the a working style of the workers. Scenario 1 represents the natural distribution of the customer to the pump islands, and scenario 2 represents the equal distribution of the customers. When I said equal, actually I want to mention that allocating the newly arrived cars to the pump islands with idle pumps. In scenario 3, workers serve only one pump island, and in scenario 4, workers serve a second pump island when needed. As mentioned before, in our simulation model, there are pump islands with 2 pumps and 3 pumps, and pump islands with 2 pumps are more closer to the entrance, so that we look the results of scenarios separately. Because in nature, customers generally prefer to do closer pumps, so that thanks to the distribution made in the scenario 2, based on the pump availability, some outputs were balanced. These outputs are the pump and worker utilizations, waiting time, and number waiting. And since there was no change in the arrival rate and the system is stable, the convenience store utilization was not affected. Actually, case 2 is dependent on the model structure. Results can be changed according to the parameters like the number of the pump, number of the workers, so that according to this model structure, scenario 4 doesn't cause any change in pump and store utilization and creates a very small decrease in worker utilizations. And it was obvious that scenario 4 reduces waiting time and the number waiting as the workers provided service to the second pump island when needed. Some examples are in the next slides. When we look to figure 3 and figure 5, we can see the balancing thanks to case 1. And as shown in figure 6, waiting time is decreased by the scenario 4. Sensitivity analysis. Sensitivity analysis was performed to measure how sensitive the outputs are to the changes in the input variables. For this reason, changes were made in the form of gradual 5% increases and decreases in each input variable, and the percentage changes in the outputs were analyzed. As a result, it is found that all outputs are significantly impacted by the change in inter-arrival rates. Moreover, it was observed that all inputs have a similar effect on the average waiting time and average number of the waiting. It has been noticed that while the factors like the cash payment rate have a significant impact on the outputs related to the store, variables like the length of the pump activities have a great effect on the outcomes related to the pump and the worker. As an example,
I think he's disconnected.
As I mentioned, my work is about the converting momentum of energy of blowing air around the local generator into electricity, which is a nice concept about the sustainable energy. And I started working on my project since I received an email from Kadir Has University. It's about 2 weeks ago. I started my working, and unfortunately I couldn't find any related studies for my topic. So I worked on it individually with my supervisor, Mr. Hamid Farangis Zadeh. So inshallah, I will do my best to prepare a nice and scientific paper for this topic. The objective of our work is about parts of generator and how it's working, and this is our idea. And the physical point of view, the different types of windmill. I will use windmill for producing electricity, and the windmill we provide 2 of them, two different windmills, which is horizontal and vertical. We will use it for the cooling system, the fan, and the exhaust. I speak a little bit fast due to I want to finish in 10 minutes. You have a break and we will start a new season. The parts of a generator, as you know, in our Kurdistan region, we have a governmental electricity and the private electricity. The governmental electricity comes from the governmental generator or the hydro and thermal power plants, or the final choice, we buy electricity from the neighborhood countries, and we will we will use grid electricity for distributing, and we will carry out the voltages and the amperes for the our country. The generator, sorry, it is we have some parts of it. We, as you know, it's engine, alternator, fuel system, voltage regulator, and the cooling system and the exhaust system. We will use it for our idea, and lubricant system, battery charger, and the control panel. So, okay, our idea is about to build a non-expensive and almost noiseless small windmills from for the exhaust and the fan of the cooling system, air cooling system, for the generators that could produce a DC electric potential. My study is about having a 2 or 1 ampere of electricity for these generators. If you have a 2000 generator in Kurdistan, or almost is above this number, we could produce for each generator 2 amperes. We have a 4000 amperes for Kurdistan. We could use it as a good source of electricity. However, I looked at previous studies that they put piezoelectric under the highways, under the roads, for having some small voltage, some small millivolts. So it's about 4000 ampere. It's a good, I think, good study for our area, and we convert the linear momentum to radial momentum of the our work. And this is a point, the physical point view, which is about converting the linear momentum to radial momentum. Okay, we have different types of windmills. Sorry, again, I do apologize. I couldn't find any resource that worked in this study area, and I will, inshallah, provide a best one. This is a fans that we can have it, whether it's horizontal or vertical one. We can use this as a vertical one. This is as a horizontal one. And this is a case of my study that is a horizontal noiseless windmill for the fan that I mentioned in here. For this cooling system, this is a fan that came out and air strongly push the air out. So I will use this is as a fan of generator, and this is our fan that we will use in front of the generator's fan, and we produce a DC current. And this is another prototypes. As a vertical one, we can use this one as a prototype. We put in the above of the generator's exhaust, and it is converting the linear momentum to radial momentum, and we can use the roll bearing, second-hand roll bearing. We can find in factories as a second-hand. It's very good due to the less friction, and we can use a second-hand metal we have in factories, like for using for tanks. We can have small generators, and we can use produce the electricity. Oh, sorry. It's our conclusion is a clean, economical, and it's environmental friendly. It's a small, noiseless, easy to assemble, to use, and recyclable. And thanks for your attention. Thank you very much for your nice conference.
Thank you, Aryan. Maybe we can start with Gökhan Hoca. And maybe Şener Hoca, if you have comments, please, because it's about your topic, I think.
Yeah, thank you, Aryan, for your presentation. It was nice. But the one thing I didn't understand, why don't you utilize that hot air for heating? Well, you can directly use it for heating, or maybe you can convert to get some hot water. And you don't do that, but you basically use its momentum to generate electricity from generator. That's interesting.
Thanks a lot. This is a nice topic, but I studied another case for our power plants that they have a. Sorry, you hear me?
Yes, I can hear you. We hear you.
Okay, thank you. We have oil power plants. We have oil refineries that they extract the oil. With oil, we know all of us. With oil, there is a gas. They flare they have a flares. And this flare, this gas, just they fire, they will burn out with nothing. It means it's a very useless thing. This flare, I worked on it, and I found some studies they could even make a hot water, or they could even make great things from this fire. And your topic, yes, is very good for having a hot water, or even we can use this hot things like they have a super. They have two supers on it. We can produce a hot air. We can use it for our topic. Yes, thank you.
Okay. Because using like hot air to run wind turbines may also cause some other performance problems, like materials may not be
may melt.
I don't know which temperature range they are suitable for operating. I don't know.
I'm working now to know how is the momentum, how much the momentum, because if the electricity demand is increased, they will load the generator, and the moment will be greater, and the heating will be increased. And I will work, inshallah. I will do my everything spiritually, inshallah.
Thank you.
Thank you.
Okan hocam, do you have any comments?
Yeah, thank you for the presentation. I'm pretty far off topic, but that was very informative for me, and nice to see a presentation from the Kurdistan region of northern Iraq. I'm moving to another meeting, so sadly I have to leave. It was a very informative session at all. It was a great honor for me to co-moderate with Gökhan Hoca, and I wish you success in the remaining part of the event.
Thank you a lot. Thanks.
Thank you very much.
Thank you, Okan hocam.
Thank you very much.
See you later.
Gökhan hocam and Okan hocam. Okay, we will end the session, and the other session will start in 5 minutes. Thank you, Gökhan hocam, again. See you.
Yeah, thank you all for your great presentations. This was a very informative session, and I wish you success with your future studies. Have a good day. Bye.